Have you ever wondered how gasoline is made and why it has that distinct smell? Today, we're going to embark on an intriguing journey into the world of gasoline production. Picture the lifeblood of our modern transportation, a complex fuel derived from crude oil, powering cars, buses, motorcycles, and many other engines. We'll delve into the fascinating process of how this vital fuel is extracted, refined, and treated to make it suitable for use. We'll also explore the science behind its distinct smell, a fragrance that's unmistakable at any gas station. From the extraction of crude oil from underground reservoirs, to the intricate refining process that separates hydrocarbons based on their boiling points, we'll uncover the secrets of gasoline production. And we'll answer that burning question: why does gasoline have that unique smell? So, buckle up for a ride into the world of gasoline. Stay tuned to learn about the intriguing process of gasoline production and the reason behind its unique smell. Gasoline begins its journey as crude oil deep beneath the Earth's surface. Picture this: vast reservoirs of this black viscous liquid resting quietly for millions of years. But how do we bring this treasure to the surface? It's all about drilling. Oil companies use advanced technology and geology to locate these underground reservoirs. Once a potential site is found, a drill rig is set up. This giant machine bores a hole deep into the earth, often several kilometers down. Now, crude oil isn't just sitting there waiting to be pumped out. It's often trapped in porous rock formations. So, we apply pressure. This pressure forces the oil from these tiny spaces into the wellbore, and from there it's brought to the surface. Once it reaches the surface, the crude oil is collected and transported to refineries where it will begin its transformation into the gasoline we know. So, the first step towards making gasoline is pulling this crude oil out of the ground. Crude oil is a complex mixture of hydrocarbons which needs to be separated. This is where the refining process comes in. Picture a bustling kitchen where a chef is preparing a multi-course meal. Just like the chef separates ingredients based on their unique qualities, the refining process separates the different components of crude oil based on their boiling points. Imagine this: the crude oil is like a hearty stew simmering away. As it heats up in a distillation tower, the various components start to boil off at different temperatures. This process is akin to the chef skimming off different ingredients from the stew at various stages of cooking. The lightest components, including gases like methane, ethane, propane, and butane, rise to the top of the tower and are collected first. As we move down the tower, the temperature increases and we collect the heavier hydrocarbons. At mid-levels, we find naphtha, a key ingredient in gasoline. Further down, at even higher temperatures, we get diesel and lubricating oils. But the process doesn't stop there. The heavy residue that remains at the bottom, called bitumen, is subjected to further processing. It's like the chef making sure every bit of ingredient is used, leaving no waste behind. The refining process is not just about separating, it's also about transforming. Some of the separated components undergo additional processes to alter their structure and improve their properties. For example, some of the heavier fractions are cracked into lighter, more useful products. By the end of the refining process, we have a range of products, from gases to liquids to heavy residues. Each has its own use in our everyday lives, from powering our cars and heating our homes, to paving our roads and even making candles. So the next time you fill up your gas tank, remember that the gasoline you're pumping has been on quite a journey. Starting as crude oil deep underground, it's been extracted, heated, separated, and transformed to give you the energy-packed fuel that powers your journey. The refining process gives us different hydrocarbons, some of which will become our gasoline. Now that we have our hydrocarbons, we need to refine them further. In the complex world of petroleum refining, isomerization and reforming play crucial roles. To understand these processes, let's take a closer look. Isomerization, as the name suggests, involves the rearrangement of atoms within a molecule. This process is used to convert straight-chain hydrocarbons into branched ones. Why, you might ask? Well, branched hydrocarbons are superior when it comes to fuel performance. They burn more evenly and efficiently, enhancing the octane rating of the gasoline. Moving on to reforming. It's a bit different, but equally important. Reforming converts straight-chain hydrocarbons into cyclic ones. Cyclic hydrocarbons, like their branched counterparts, also have higher octane ratings. This is because their atomic structure allows for better compression, which leads to more efficient combustion in the engine. Both isomerization and reforming are catalytic processes. meaning they use catalysts to speed up the chemical reactions. The catalysts used are typically platinum or other precious metals, which are chosen for their ability to withstand the intense heat and pressure involved in the process. But wait, there's more to refining gasoline than just improving its octane rating. We also need to consider the environmental impact, which brings us to hydrodesulfurization. Sulfur compounds naturally occur in crude oil. However, when they're burned, they can produce sulfur dioxide, a harmful pollutant that contributes to acid rain. To prevent this, we use hydrodesulfurization. In this process, the sulfur compounds are exposed to hydrogen under high temperatures and pressures. The hydrogen reacts with the sulfur, forming hydrogen sulfide, which can then be safely removed from the gasoline. So, through isomerization, reforming, and hydrodesulfurization, we can transform crude oil into a cleaner, more efficient fuel. These processes not only enhance the performance of the gasoline, but also make it more environmentally friendly. After these steps, the gasoline is free from harmful sulfur compounds and has an improved octane rating. The gasoline is almost ready, but there's one more step. At this point, our gasoline needs a little boost. Enter additives. These are special ingredients mixed into the gasoline to enhance its performance, stability, and combustion characteristics. Think of additives as the spices in a culinary dish, enhancing the overall flavor and impact. First up, we have detergents. These little cleaners help keep your engine clean by preventing deposits from forming on vital engine parts. Next, we have antioxidants. Just like the antioxidants in your blueberries, these compounds prevent the gasoline from oxidizing and forming gum-like substances that can clog your engine. One more important additive is the anti-knock agent. These guys help prevent engine knocking, a common problem that can seriously damage your engine over time. So these additives are like the secret sauce that takes our gasoline from good to great. With the addition of these additives, the gasoline is now ready to power our vehicles and engines. Ever wondered why gasoline has that distinct smell? Well, let's dive into the chemistry behind that characteristic odor. The primary culprit is a compound called mercaptan, also known as thiols. Interestingly, mercaptan isn't added to gasoline for its scent. It's actually added to natural gas and propane to give them a detectable smell for safety reasons. However, in gasoline, the distinct aroma often comes from other components present in the fuel. Gasoline is a complex cocktail of hydrocarbons. When gasoline evaporates or is released, unburned hydrocarbons waft into the air, contributing to that recognizable smell. Picture a gasoline spill at a gas station. The liquid gasoline evaporates quickly, and the unburned hydrocarbons make their way to your nose, signaling to your brain, "Ah, that's gasoline." Moreover, gasoline contains volatile organic compounds or VOCs. When gasoline evaporates, these compounds become airborne. VOCs, which include benzene, toluene, and xylene, play a significant role in giving gasoline its distinctive odor. These compounds are quite volatile, meaning they evaporate easily and disperse into the air we breathe. When gasoline comes in contact with air, its volatile components disperse. This process releases the odor into the surrounding environment. It's kind of like when you open a bottle of perfume. The moment the cap is off, the volatile components of the perfume disperse into the air, and you get a whiff of the fragrance. However, while the smell of gasoline is something most of us can easily recognize, it's worth noting that prolonged exposure to its fumes can be harmful. Gasoline vapors are flammable, and inhaling them in excessive amounts can pose health risks. Therefore, it's always important to handle gasoline in well-ventilated areas and follow safety guidelines. So the next time you smell gasoline, you'll know it's the unburned hydrocarbons and volatile organic compounds at work. It's a complex blend of chemistry and sensory perception that all comes together to create that unmistakable scent. We've learned how gasoline is made and why it smells the way it does. We started with the extraction of crude oil, a complex mixture of hydrocarbons from underground reservoirs. This crude oil then undergoes a refining process where it's heated and different fractions are collected based on their boiling points. To enhance the octane rating of the gasoline, isomerization and reforming processes are employed. Furthermore, sulfur compounds are removed to reduce air pollution and prevent damage to catalytic converters. To improve performance, stability, and combustion characteristics, various additives are incorporated. As for the distinct smell of gasoline, it's primarily due to a compound called mercaptan or thiols, along with unburned hydrocarbons and volatile organic compounds. Remember, while the smell of gasoline is familiar, prolonged exposure to its fumes can be harmful due to its flammability and potential health risks. The next time you fill up your tank, you'll have a better understanding of what's in your fuel and why it smells that way. Thanks for watching.